Right, then let's begin. So it's already 5. We have 45 minutes. Let's see how much we can cover. So what is computer vision? So some of you might already know it's like the ability of computers to understand visual data. And by visual data, we mean it could be images, it could be videos. And again, images can have different forms. They can be grayscale, they can be RGB, and they can be infrared as well. And same goes for videos. So the goal is like how we can automate tasks which human visual system can easily perform. So can we like rely on machines to do that? So for example, this is a simple example where we have an image. We can see like different objects in this image. And as a human, it's very easy for us to like tell which object is which. We can easily recognize them. We can say that here's a bottle, here's a laptop, or here's a like cup. And we can also easily draw boundaries of these objects. And so the question is, can this be done by any automated machine or a computer, as we call these days? Now, if we try to understand, like, if we try to look at the bigger picture, where computer vision stands, if we look into like other research areas or other fields, so it's a nice graphic where computer vision is at the center, and it overlaps with like most of the other disciplines. It overlaps with biology, we have psychology, we have computer science, we have mathematics, we have physics and engineering. And if you look at these smaller segments of these, so cognitive sciences, neurosciences, so you will find like some overlap with these areas like robotics. And as you might be noticing, there's no overlap with speech. So that's entirely different because speech is like another modality and vision is another modality. So it might happen that you are solving the same task or the same problems when you're using speech as you're using like a vision, but then there is no overlap between these two. This doesn't mean that you can't use these two together, but then that will be like an interdisciplinary area. It won't be computer vision. So visual perception, if you try to understand this, how for sure we can say that if you're seeing some object, it's actually there. And sometimes it happens that we are looking at something, but we are not seeing, we're not perceiving it. And so there are some other questions to ask, like why do we see like colored objects? So these are like some very basic questions which lead to different problems and solving different issues when we try to like tackle this computer vision or ask the computers to solve the problem which human vision can do. So this is a formal definition. That's fine. We don't have to cover this. So it's a multiple step process. First, we have the vision. Then there's some cognitive activity in the brain. And we also need like acquisition of some kind of knowledge to infer what we are saying. So someone has said like, it's analogous to taking a picture. So let me just minimize this. All right. So if we look at a human eye, then if we have an object, we have a lens, then an image is formed, and whatever image is formed based on that, we perceive something, and then we try to make sense like what actually we are seeing. Similarly, if you look at the camera, we'll have an object, we have a lens, and the image is formed, and this image is like which is like sent to a computer or which is like perceived by a computer. So there is some analogy here, and the important part is how we are going to perceive what we are seeing. So those are the problems which we will tackle in computer vision. So as I said earlier, we might be seeing something, but we might not be perceiving it, and it happens a lot. So just looking at something doesn't mean that we are also perceiving it. So for example, if you look at this picture, so can you see something? Now, if I tell you that there is a dog, so if you were not seeing this earlier, now you can make sense of this. Okay, there was a dog, and now you can see it, right? Even though there is no boundary. So let's take a look like what computer vision is and what human vision is. So for human vision, we have a sensing device, which is our eye, and then we have an interpreting device, which is our brain. And let's say if we're looking at this picture and we want to make sense of it, so we can say there's a picture, there's a person, there's a trash can, there's a light bulb. So we can describe this picture very easily. And this is not just like based on what we are looking, it also depends on like what is the interpreting device, what kind of knowledge a brain has to do that interpretation. And if we look at computer vision, again, we need a sensing device. It can be a camera. Then we need some kind of computing device. It can be a computer or something else, which will make these interpretations. So in these tasks, when we are looking at something, so why we try to interpret it. So there are different interrelated things, and you can say that if you want to survive in an environment or if you want to just navigate through an environment, then we should know like where we are. We should know like what are the objects which are surrounding us. And if we want to interact with them, like we want to pick some objects, then we have to recognize them. Because if it's like fire, then you don't want to touch it, right? So similarly, there are more examples. You want to differentiate friends with enemies. Now, the goal of computer vision is to bridge the gap between like what you have in image pixels and what those pixels represent. So this is an example, it's a grayscale image, and this is like what we are seeing. And it's very easy for us to interpret like this is a person who is reading this book. There's another person maybe sitting down, even though these like this is very blurry. So this is like what we see, and then based on what we are seeing, we perceive something. So if we just take a small block of this, so it will look like something like this. It's a grayscale image, and this is like what the computer will see. It will just see some random numbers, not random, but it will just see some numbers. And there's a big difference. So the computer will have to make sense of what it is seeing based on these numbers. But we have this nice picture here, which makes it easy for us like to interpret it. Now let's see like what's a digital image. So it's a two-dimensional array, and we represent this as a matrix where we can have some n rows and some n columns. And then each value in this matrix represents each pixel in this image. So that's what we call resolution of the image. So if you have n cross m by image, or the resolution is n cross m, then we'll have n rows and m columns, and we'll have n cross m pixels in that image. So if it's a grayscale image, then that will have just a single value for each pixel. So a scalar image will have integer values between 0 to this range, where a is like the bit level of that image. So for example, if the image is 8-bit, then a will be 8, and this is going to be 128. So sorry, 256, and then the values will span from 0 to 255, where 0 will mean black and 255 will mean white. So the pixel will have values between these two numbers, and depending on that value, you will see like see some shade of gray. Image can also be 1-bit. It can, and we call that a binary image. So it can be just black or white. So here we are showing like some samples. It's a grayscale image, and depending on like what's the bit level, you can see the clarity of the image is changing. So in this case, we have 256 values. So you can see like it's a very clear image. And as we change the bit level, so for this, we have just 4 colors. And if you move further, like just make it 1, it will be just binary. So we won't see like this a grayish color. It will be either black or white. So that's how we represent a grayscale image. And if we move on to a colored image, which we call RGB, it will have 3 channels. The only difference will be instead of single channel, it will have 3 channels. So at each pixel location, we'll have 3 different values, and those values will correspond to either red, green, or blue. And the rest of the things remains the same. So if it's 8-bit, then for each pixel, for each channel, we'll have like 256 values. Now, in a human vision system, cone is like something, we call these cone cells. These are responsible for like color vision. And we have 3 different type of cone cells. So L is like longer wavelength at a higher wavelength. Then green is somewhere at the middle, and blue is at like the smaller wavelengths. I will cover like more details of this later. So usually we have 3 cone cells, and these are like large, medium, and small, and corresponding to red, green, and blue. And this is the range of the wavelength. But some people have like 4 cone types. What it means is they can see like more colors than normal people. So there is a test like you can conduct that and see whether you have 4 or 3. And in fact, some also only have just 2. So they see like less colors. And I think 2 or 25% of like people on Earth, they have just 2 cones. So this is interesting fact. And so we all know like this color vision has evolved over millions of years. We have like different wavelengths of light, and the visible spectrum is between 400 and 700. You can see like how it changes as we move from blue to red. So this is like the same chart I showed you earlier. So 400 to 700. So blue is like the smaller wavelength, then green and red will have the highest wavelength. It's on the right. So this is interesting, like if there's no light, you won't see anything. Everything will be black. And if it's just a gray color, we can only differentiate between like maybe 20 or 30 different gray levels. But if it's RGB, it's colored, then it's a lot more than that. So again, this is like just showing the wavelength which corresponds to these colors as we move from red to violet. And this corresponds to the same plot which I showed earlier. And this is just like a nice diagram of human eye. So I was talking about different cone types. So those cone types are actually located at this location, which are responsible for this color vision. And a normal human eye has roughly around 6 to 7 million cones. So there is like another cell type which is called rods, which we have 120 million, and they're responsible for like the brightness, not the color part. So if we check the distribution of these cones, so 64% of these cones are red, 32% are green, and about 2% are blue. So if you will look at this plot, you can see like this nice Gaussian curves, very thick, right? As compared to the blue one. So, all right, so that's like just some nice details about human eye and colors. Now, why should we study computer vision? So you should have some good motivation. So it could be like you just find it interesting. That's fine, you can study it. You can just study out of curiosity, or it could be just your course requirement. And all of this is fine. But I will give you like some more interesting points why you should be studying computer vision if you're doing engineering. And so there are a few important things. So the recent advancement, there are a couple of recent advancements which has actually created a very like positive environment in computer vision community. So earlier it used to be done only in academics by professors and grad students, PhD students. And it's not like I'm not talking about way back, like decades old. It's like maybe around 2010. So this was the scenario. But what has happened is due to the evolving nature of deep learning and all the hardwares we have. So not just academia, all the industry people, everyone is working on computer vision. So like all the top industries, they have research labs which are looking into computer vision. They are doing research, they are publishing papers, whatever like academics used to do, these guys are also following. So what changed? Why this happened? So the first reason is like emergence of deep learning. You all might know about that. The second thing is advancement in hardware. So we have like available these cloud services where we have GPU resources, we have storage services where we can store our data. And the most important thing is like advancement in this GPU technology, which allows us to like train our deeper networks. And we're going to cover that later in our course. The other important fact is the availability of large scale data. So the camera technique has evolved a lot. I mean, 20 years back, you had like that rolling camera, right? So I mean, you can't take a lot of pictures using that. But today you have camera right in your pocket, like in your mobile phone, and you can take as many photos as you want. You can capture as many videos as you want, and you don't have like space limitation. You can store as much as you can, and that has led to like large scale data, which is being made available maybe via social media, or there is like different platforms. You have Google Images, you can get images from Flickr, you can get videos from YouTube. So there is no like limit to how much data you can capture. So that's like the third thing which has changed. And these are some of the data sets which are widely used in computer vision community. And you might be like, you will get familiar to these like as we move on in the course. So ImageNet, this has I think around 15 million images. Again, Open Images has 10 million images. This one, the name says it has 100 million images. And of course, this also had like around I think 1 million videos. So this YouTube 8 million, it has 8 million videos. Similarly, we have Kinetics, we have AVA. I think these has less than a million videos. But so these are like the large scale data sets which are available to us to perform research. Now, so apart from those three changes, what else? So that has led to like a big change in like how investment is being made in the industry. So if we look at like how much people are investing in computer vision, so this is like 2011, this is 2012 where like the deep learning emerged. And this is a plot like not recent, but 2017, you can see like how this chart is growing and how much is being invested in computer vision industry. So it has changed drastically. Now, so another interesting fact. So computer vision, so we do research, we publish papers, and so we publish them like either in conferences or journals. So CVPR, this is like a computer vision pattern recognition conference. This is one of the top venue where we publish computer vision research. And this is showing a ranking of all the conferences, all the journals from the whole engineering field. So this is not just computer science, this whole engineering. So CVPR is at the top. So it means like a lot of research is being done in this area. So these are like two metrics which is used to measure how good a conference is. So this is H5 index, and H5 index is, so this 5 indicates number of years. So H5 index means how many papers in the last 5 years have been published in this particular conference, which have more than 299 citations. So citation is something which is like used to measure how good a publication is. So when you publish a paper, and if other peoples are citing your work or mentioning that you did something or something, so that's called a citation. And if you have more than like 299 citation and you have 299 such papers in last 5 years, so that's how you compute this index. And H5 median is nothing but like, if you take all those papers, so what was the median value of the citation? So it was 5, it's 509, and that's like much higher if you compare with other journals. So you can see like this is not computer science, it's advanced materials, right? It's entirely different area. Again, this ICLR, this is also computer science, and we do publish computer vision research in this conference as well. Again, this is like on the top. So this is another motivation for people who are going to graduate and are aiming for a PhD or higher studies. So this is a really nice topic to start working on at this time. Now, again, talking about the same conference, CVPR. So this shows like how many papers were submitted and how many papers were accepted in that particular conference. So this showing like way back in 1983. So if you have a look, like until 2009-10, you have like maybe 1,000 or 1,500 papers, but today there are like around 5,000 or 6,000 submissions. That's a lot. And even like the accepted papers, that's increasing. It's 1,500. It's way more than like what was submitted into these conferences. So it's changing drastically. And it's not like just true for this conference, it's like true for all the other computer vision conferences like ICCV and ECCV. We are seeing like around 5,000, 6,000 submissions each conference. And this conference, oh, by the way, like it happens like every year. So considering that, it's a lot. Again, this is showing like how many people are attending this conference. So again, it's increasing a lot. And this is happening because a lot of industry people are going to attend these conferences because they need like these latest techniques to build their products. Of course, there was a dip this year, and this was due to like because the conference was conducted online. Okay, so that was something to motivate you why you should do computer vision. And before we move forward, I'm going to show you like a short video. It's a video about a police chase. I think it's from last week. Let me see if I can play this. It's an hour-long video. It's an hour-long chase. I'm not going to show you like. Let me pause this first. Yeah, I'm not able to mute it, but that's fine. So this is a police chase. It was a high-speed chase. This is like I think Dodge Challenger. I don't remember the exact model. So it tops at I think 200 miles per minute. And okay, let me see if I can. Okay, that's better. So what happened? It outrun like the helicopter, all the police cars, everything. So it was out of sight. And then I'm showing you this because, of course, I don't think a lot of computer vision was used while this chase. But what you have to do is that you have to think about how computer vision could have played an important role in this chase. So there are like a couple of helicopters following this car. So this is like a UAV camera like zoomed into the car. So the helicopter is actually very far away. And so what happened, it outrun, and I think it was out of gas. So it stopped like somewhere close to a forest. And then the guy like came out and he was hiding somewhere in the forest. So this is like all the recording which was done by the helicopter, and of course like it's a very high definition camera. It was able to zoom in like to very far distance. And then what happened, they ran like infrared cameras in the forest. So it's a very, very huge forest, like very dense. And I mean, I don't think if you just manually look, you will be able to do that. So they ran infrared cameras and they were able to capture like the heat signals. And later on, they find out that the person was actually hiding under a tree. Yeah, he just came out, just talking on the phone. I don't know what he's thinking. That was funny. All right. So what this has to do with computer vision? So I'm not going to answer that question. You'll have to think about while we move forward in this lecture, and later towards the end of the lecture, I will ask you like at what stages in the whole video or this whole chase you could have used computer vision and make it more efficient, or even like is it possible that we don't need actual like policemen or the helicopters following that person? Can like the autonomous UAVs or the autopilot cars could have done this job? And if yes, what were the techniques and what were the problems that would have killed. So those are the questions you have to answer. So now I'm going to show you like some applications which are possible today. So all of you, I think, are aware of Amazon Go, and it's a nice store in Seattle, I think, where Amazon employees, they can just move into the store, just scan the card. They will take like whatever they want, and they will just come out. So no billing, nothing, hassle-free shopping. So how is this possible, and how is like computer vision playing a role? So this is like not future, this is like something which is being done today. So let me show you like some more applications. So these are applications in retail. So we all know like how we have like automated machines that can just scan our items and then just pay the bill and move on. But how is that possible? How like they are relying on customers, whether they will cheat or not. So this is something, this is stop lift. So they are consistently monitoring it, and if someone is going to steal, so they're going to detect that. And this is like pure computer vision. And again, this is possible today. So this is another interesting application. So this is in clothing industry. So if you go to a shop and if you don't want to go to the changing room, they have this mirror where you can just, okay, let it play. So they're using this kind of camera. It has a lot of sensors. So what you can do is you can just stand in front of the camera and choose like whichever dress you want to try on. So again, this is computer vision, and again, this is possible today. All right. So other examples, other applications I have is like from self-driving car. Again, you must be aware of this as well. So let me skip this one. So this is interesting. This is autopilot. You don't have to control the steering. Again, the important question is, of course, this is like something more than computer vision. But the interesting question is how computer vision is playing a role here. And because of course, when if it's autopilot, we are not watching the street, the car is, and it's making all the decisions. So to make all those decisions, then it should have like a good vision system which can perceive what is happening in the road. So it has a very big computer vision component. Right. We can skip this. Okay. All right. So those were applications. Now let's talk about, to make those applications possible, what are the different computer vision tasks which we need to solve first? So the most basic computer vision task is object recognition. And the problem is, if you have an image, so can you recognize if any particular object is present in that image or not? So for example, you have some sample images here, and the question is, does these images contain an image of contain a person or not? So we can easily tell like, yeah, all of these images have, we have people here, right? Everywhere in all the images. And this one, no. So this problem is like the most basic problem. We call this object recognition. We want to recognize whether a particular object is present in the image or not. So moving forward, we have object localization. And what we have to do here is, of course, we have to solve object classification or object recognition. But in addition to that, we also have to localize where that object is present. So again, the same set of images, and you can see we are not just saying that, okay, we have a person here, we're also localizing where the person is. We call this object localization. So this is another example of if it's just humans, and there could be like multiple humans in an image. So we have to draw bounding box or maybe draw some kind of boundary. So this is human detection, but again, it's the same category, object detection. Now, if you want to make it more complex, we have semantic segmentation. So in semantic segmentation, we have to identify all the objects present in the scene. And so it's like more complex than recognition, even more complex than detection. So it's not just detection of single object, it's telling you what object is present at each pixel location. So for this particular image, we need something like this. So if this is a green, we can say that, okay, at this pixel location, we have a grass. If it's blue, we can say at this pixel location, we have a person. So this is called semantic segmentation. And of course, there are different variants. We can just do the segmentation, that's also fine. But we also may want to like differentiate between different instances. So we call that instance separation or instance-based segmentation. So in this case, we have like labels for all these colors: grass, person, duck. So you can see that we have a misclassification here. This little boy, he's being classified as grass because he's green. We can make it more complicated, and we can describe like what is happening in the scene. So if we have these ducks, so we can classify like these ducks are actually looking for food, or this person is actually feeding ducks in the park. And there are a lot of people, these people are walking in the park. So this is like descriptive semantic segmentation. This is like showing some results. So we have a work, a recent work 2017 from CRCV, and where we solved this semantic segmentation problem. So the center one, or like the results obtained using that method. And the interesting thing was this was semi-supervised. We used like very few labels for that. So another interesting problem is semantic part labeling. Now, earlier we saw that we want to segment whether this pixel belongs to a person or not. Now we want to say that which part of the body that pixel belongs to. So if it's face, we'll have to say it's face. If it's eye, we have to say that this pixel belongs to eye. So it's like going into more detail. Another interesting problem in computer vision is face recognition. And today, this is kind of solved problem, because whether a face is present in the image or not, it's very trivial for a deep learning model. And it might be like there in your camera phones, right? If you pick up your camera and you try to take a portrait, it will detect for you whether a person is present or not. It will just draw a rectangle around the face. So it's kind of solved. And there are like a lot of controversies around this as well, because of privacy and all. But it used to be like a very interesting problem. So, but we can have different variations of that. For example, you can have open universe face identification. So given this image, can you identify like a person which is important figure? So for example, we have Barack Obama. But again, given the same image, we are not interested in like important figures. We are just looking for our friends. So can we locate those? So it's just like variation of face detection. And again, this is another interesting problem. Can we find like a person in big data set of faces? For example, if you're looking for Angelina Jolie or George Clooney, so you have to like find images which belong to these guys. So closely related to face detection, we have facial expression detection. So if it's surprising, whether it's smiling. And there's another interesting application. Can we detect like if we have fatigue like in the face? So this is mainly important for self-driving cars, where we want to see like if the person who is driving, whether he's fit or not. So we can detect like whether the eyelid is like closed or not. So we can figure that out if there's occlusion where the person is looking. So that's a nice application. Again, we can have lip reading. So we have just video of this lip, and if that person is saying something, can we determine like what this guy is saying? So that's called lip reading. And this is another interesting application where we have high density crowds. So if you want to track these people, that's very challenging. The other interesting aspect is if you want to count like how many persons are present in this gathering. So we have a method here which actually does a pretty good job. So the actual number of people are 634. The method predicts 640, which is pretty close. And this is like even denser. So we have around 1428 people here. The system predicted 1468. This is even denser, so even more challenging. So there are around 2,319 people. The system predicted 2,400. So that's pretty close. And we will see like why this is easy for a computer to do, but difficult for us as a human. It will take a lot of time to count these people. This is another interesting application where we have visual business recognition. So this is pretty recent. If you point your camera towards some store, then you can pull information from like all the social media from Google Maps and provide you more details just based on the visual. And there are tons of other applications in biometrics. So this facial recognition is used like log into your system. All of you must be using that. Smile detection, it's already there in your cameras. And there are a bunch of other applications like in gaming industry, we have Microsoft Kinect, we have the Sony iToy, and it's also used like in assistive technologies. So that was all about images. Let's move on to videos. So video is nothing but like a sequence of frames. And usually most of the videos these days, they are 30 frames per second. And it's just sequence of frames. If you play that sequence, you will get the video. And let's talk about, so I will quickly go through this. We don't have much time. So similar to object recognition, we have action recognition in videos. So given like a bunch of videos, can we recognize which action is happening? For example, in this one, the person is cycling, here people are playing volleyball. So instead of object recognition in just images, we have like motion as we like move from one video frame to another, and we have to detect like how that motion is evolving and which action is being performed. So similar to object detection, we have action detection. Again, we have to also localize where the activity is happening. So this is a nice paper like we published in NeurIPS, I think in 2018, using capsules. So this is like output from that system. And it can localize these actions pretty well. Another interesting problem is video segmentation. And again, this is like similar to what you had in image segmentation. We talked about semantic segmentation. So can we draw these fine boundaries for these objects along the video as we move from one frame to another? So again, this is like not the actual segmentation. This is segmentation which was generated using one of the system which we have developed. This is another interesting problem in videos. So if you have an action, like a person is, let's say he's bending over and you're capturing it from one viewpoint, then can you try to predict how this action will look like maybe from another viewpoint? So maybe from this viewpoint, this is like the frontal view. So this is the ground truth. And we have developed a system which can actually predict this. You can see it's kind of blurry, but it has a good sense of like how that action will look like from a different viewpoint. So this is like more of video synthesis. And again, so detection, but just in aerial videos. Another interesting problem is tracking. So if we have an object, let's say we detect it, so can we track that object in the long video? And of course, we can have multiple objects. So can we track them? So again, this is like not the ground truth. This is a system output of method which we have developed here at CRCV. So it's pretty cool. Like the scene is pretty dense and it is able to track all those objects. Okay, so a big application in videos is video surveillance, and we have video monitoring, and the problems which are relevant there are object detection, we have object tracking, then we have object categorization, classification, and then action recognition. So all the problems which we have talked about so far, they are required to solve the problem of video surveillance. So here we are seeing like some sample videos where we can see that we are not only detecting the object, we are then classifying the object, and we are also tracking those objects. We have these tracking IDs over those people. So as we move from one camera to another, these IDs should be consistent if we really want to track them. Now, the interesting question is, how can we detect an object in an image? So a simple approach which used to be like done, I think maybe 20 years back. So if we have a chair and we want to find or detect this chair in this image, what we do is we just put this image of the chair over all the possible locations and find like a pixel to pixel match. So it can be correlation. So the location where the matching is like pretty high, we are seeing this white spot. You can say, okay, the chair was present there. So this is like how it used to be done. But if we look at like in real world scenario, if you have an image and you want to find chairs, that's a correlation. So it's saying all those are chairs, so it won't work. Of course, it's not efficient and it's not effective, but this was like the very preliminary idea. Now, instead of comparing raw pixels, what we do is we try to find a more robust representation of that image. And we will learn like in the lecture when we will talk about features. And then we, instead of like comparing pixel to pixel, we compare those embeddings or those features for detection. And we have different kind of features. We'll also cover these. This is another way to represent images, which is called bag of words. So we just divide like an image into different regions and put them in a bag, and we create a histogram out of that. So we say like, okay, these type of patches, we have that many, these type of patches, we have that many. And then we can do a one-to-one matching between these histograms to find out whether that object is the one which you're looking for or not. The issue here is that since it is a bag, we don't care where that object was located in the image, and it's a big limitation. So now if we compare like how computer vision can solve some task versus how human vision can solve it. So there are tasks which are easy for humans and there are tasks which are easy for computers. For example, computers can easily like count these people, right? Pretty fast. But if we ask a human to do that, I think he's going to take a lot of time. So briefly, like tasks which are global, humans are better than computers. By global, I mean like if you have to describe some image, then it will be very difficult for an image, for a computer. But if the task is local, then computers can do a pretty good job. The local task is like counting how many people are present in this particular image, or like just counting certain type of pixels in an image. So just going through a brief history. So if we have shown this image to computer 50 years ago, it will just say out of memory because we didn't have that much computational power back then. 25 years ago, if we have to do object detection, these are like some of the results which we got. I mean, it was impressive that we can process this image, but of course the results were like very not satisfactory. 15 years ago, we have this face detection in our cameras. 5 years ago, we developed a system where we can count that many people in the crowd. And today, what we can do using computer vision, it's very fascinating and very scary as well. So probably I think you can watch this video after the lecture. So you can see that this is like the original video and we can modify it. We can like make people say something which they never said, and which is kind of scary, and it is being used a lot these days. Maybe it like for political gains or for whatever gains it is. And so this is what computer vision can do today, and it's really impressive how the progress has been made like in the last 8 to 10 years. Okay, so any questions? We are just in time. So probably we don't have too much time for questions. What we can do is you can ask your questions via chat, and probably we'll try to answer on web courses. Or what you can do is even better than that, just put your question on the web courses discussion forum, and we will answer it over there. But we can take like 1 or 2 questions if there are any.
Hello?
Yes.
Can I ask what kind of or what type of library do you want us, do you recommend us to download in our programming language, Python or MATLAB? Like, which is the best for computer vision and deep learning?
So again, so I said this earlier as well regarding programming language. So personally, I will recommend you to use Python, but we are not restricting you to use Python. I mean, you are open to use any language you want. But if you want a recommendation, I think I will recommend Python. Again, regarding the framework for deep learning, we are not restricting you to use like any specific platform, but the tutorial which we will provide in the coursework, it will be on PyTorch. And I will recommend you to use either PyTorch or Keras. Both are fine. Both are like, I think, equally easy, I will say, to pick up. But again, if you want to use TensorFlow or something else, or Lua, you are most welcome. You can go ahead with that as well.
All right, thank you.
Yeah. Okay, so one question from the
chat group.
So will these slides be updated on the course material page? Yes, these slides will be there on the web page.
Will there be machine learning in the course?
Yeah, so I said that earlier. I mean, it's not a machine learning course. It's not a deep learning course. So we will only cover those topics which are required for computer vision topics, which we will discuss in this course. So there will be some machine learning, but don't expect like that to be in too detailed. So did that answer your question?
Yeah, thank you.
So I can say a bit more about that. So machine learning, we will cover what CNN is, again, because those are relevant to computer vision. We will also cover neural networks, not because it's relevant to computer vision, but that will help you in understanding CNN better. But what we will not cover is, we won't cover like network optimization. We won't cover like classical machine learning methods like clustering. We might cover nearest neighbor for one of the, I think, problem in one of the lecture. But again, we are not going to cover like clustering task or classification task very comprehensively. So when you're talking about classification, we will only cover image classification. I hope that answered your question. So Miles, I think you joined late. Yeah, yes, the lectures will be recorded and the videos will be uploaded to the course webpage. Look at like the page for the schedule. Both the slides as well as the videos will be uploaded there. All right, so we are already out of time, and any other question you have, just put it on like the discussion in the web courses. We'll answer it there. So don't hesitate. Whatever question you have, even if it's very simple, don't worry about it. Okay. So I look forward to you like for the second lecture where we will cover like the basics of linear algebra. All right. Till then, bye. You can end it here.